So from here, after the leveling lab, we'll be talking about a traverse. And when we're referring to a traverse, we're looking at something that is a border of not only the proposed building that you'll be looking at or designing, we'll be also referring to the location of the construction, how much we can enclose in that as well. So that includes the whole entire portion of that. So I drew out a small traverse right here. And from here, in theory, you want to show that every single portion of what we're showing here is going to match up perfect. And that's in an ideal world. In the real world, when you have a starting point and you reach that same finish point, if we bring that out, you'll have the same point that's there. And that traverse starts out in that direction. When it comes all the way back around, it may not finish directly at that point right there. It may finish somewhere right here instead. And this is what we refer to as the ratio of error. So that's the amount of error that's actually found in the human case just because of human error and that we don't really have a common environment to have something as perfect as we really want it to be. In smaller scenarios, that could be the case, but when you're looking at a large traverse, this error can be minuscule, but it's there, and we need to take an account for it. And so from here, we'll have something that we refer to as, I know this may be small to see, but we have things that are referred to as latitudes and departures, and that's where we get into this type of component here. So when we're looking at a traverse, we want to make sure that we understand a north direction, and that kind of gives us our entire reference from there. If there is not a north arrow given, typically there is, because when you're actually on site, you can determine where north is and then take your angle from there. However, if you do not have that information, you can have a starting point and assume a north direction going 180 degrees, 180 degrees to whatever length you have. This is referred to as an azimuth. You assume an azimuth of 180 degrees for your angle and then continue from there. And this will help you determine what these interior angles are of your traverse. And so from here, we know since this is 180 and this is all collinear with one another, we know that this right here is 180 degrees. From here, you take whatever angle you calculated in the field, whatever that may be, it's going to be an acute angle, but whatever the actual measurement is, we'll refer to this as angle A, because this is at point A. We'll just call it that. And we'll label these B, C, D, and E. So from here, we understand that we have what is known as a back azimuth of 180 degrees. To get a front azimuth, we'll be referring to this location right there. In order to get that front azimuth from A to B, we'll refer to that as azimuth AB. This will be equal to this back azimuth here, which we already know is 180 degrees, plus whatever angle you have for A. And that gives you this length right here. As we progress through here, we can determine what this back azimuth will be, and that is just a 180 degree difference between whatever we determined here. So whatever this is, we will refer to this as a back azimuth of AB is simply whatever that azimuth is minus 180 degrees. And you can see that there is all that we're doing is taking that and then subtracting that. These two portions are equal, and then we are taking that back azimuth. And so now we just repeat that process as we progress through. We now know a back azimuth, and we have an interior angle at B. As we progress through there, we can find out what the back azimuth is, which is right there. So all we need now is an azimuth from B to C now is what we're referring to, equals your back azimuth that's already calculated here from A to B is what we're looking at, plus the interior angle at B. And we progress through here, and determine all these interior angles relative to your north. That's essentially what we're doing here, is taking all these interior angles that are relative to themselves and the things that they are next to, and converting them into an angle that we can find that's all relative to the same measurement. And that's really what's being done here, since it's all relative to this point right here. As we progress through there, we can see that we have particular points, C, D, and E, and they will all have this particular angle associated with them. A certain distance is already predetermined because that is something that is done in the field. We already know what that is. As we progress through here, we need to determine what these, in this case, latitudes are. We will look at latitudes and then departures. It's the same process as we progress, but we'll talk about that at a different time. When we're referring to the lateral portions, the latitudes, this is what we're referring to when we are looking at our traverse and we are looking at all the vertical components of this distance here. So it's kind of looking at right angles in that sense. When we are referring to these portions, everything needs to be converted to vertical and horizontal components relative to the north arrow, not necessarily on the page. A lot of people, when they get to this point, they want to see it like this and draw their vertical and horizontal like this. That is not necessarily the case because it's not relative to where the north arrow is. Your latitudes and departures come into this direction. Everything needs to come parallel in your latitudes, and all your departures need to be perpendicular. So in this case, your very first point right here, you should have no departures because everything's collinear with one another. That should just be one vertical component, and that's your latitude. And that's whatever distance this may be. As we progress, we are going to see that this has an actual vertical and horizontal component. We need to determine what these angles are based on everything that we learned from the previous part. As we progress there, we know what this interior angle is. We know that this needs to be 90 degrees. We could take that difference and find out what that interior angle is on that side. From there, we can determine, based on a known distance here, so we'll call that a D, we can find out based on the Pythagorean theorem and just like sine, cosine, tangent, those SOHCAHTOA laws, what this component is and what this component is based on that interior angle right there. As you progress through, we can find out the north and south. This is where we start to take into consideration the direction of where we're going. This can be started at whichever point you really want, but ideally what we are referring to here is we want all of the angles, or we want all the angles to match up so that the interior matches whatever distance or whatever angle that may be for the polygon that it is themselves. So for a triangle, that would be 180 degrees. For a square or rectangle, that's 360. And we have to make sure that all these angles match up to there. So that's why we determine what these interior angles are and then follow through. As we're going through this, we want to make sure that the sum of the distances that are going south are equal to the amount that are going north. In that case, that helps so that we know that all the points are going directly to the same spot. And that's where we get this error, because the south direction and the north direction don't necessarily equal each other. And that's where that error comes in. This is what we do to correct that. As we progress, we'll notice that if we start from here, we'll just start at E. If we come down here, we know that north is the opposite direction. So we know that this is a south. This whole thing's a south. There's no east or west on this. And we're just looking at the latitudes themselves. As we want to go from A to B, there is this part that it wants to go up. So this is a north. As we progress, we'll see that we'll have another north right there because that wants to keep going up. And with this, we will see that this wants to go up as well. And that'll be a north. So with this setup that we have here, we have one south and 1, 2, 3 norths. So whatever that may be. So one south and then 3 norths that we'll have here. These souths, this one south has to equal these 3 norths. And that just makes sense if we want to keep everything in equilibrium. As you progress there, that may not necessarily be the case. And as we go through, there is a correction factor that we will associate with each point here. And I'm sorry, what were you saying?
It's 2 south, right?
2 souths? Nope, 1 south. If we're going here, south, and then coming up north, north, and then north, that should be. Oh, you're right, there is another one. You're right. This one right here. Another south. You're right. I apologize.
We can go from